Good morning, everyone. So in the last chapter, which was chapter 7, we discussed about one-dimensional flow. We talked about Bernoulli's equation, we talked about Darcy's law, which is really applicable only when the soil flow through the soil is laminar and steady state. Most of the engineering problems are not really one-dimensional problems, so we need to really think about when the problem we can convert to two-dimensional or three-dimensional. So chapter 8 of your book is going to be about multidimensional flow. And in this lecture, I am going to describe what is really the governing equation for multidimensional flow. And then how can we solve these governing equation, which can be done by graphical tool, and that's what we are going to focus on. We can do it analytically, and we can do closed form solution, and also nowadays we can do numerical. But that's not going to be the focus. Focus is going to be graphical tool. And it's a very powerful tool in spite of we can do all the numerical analysis nowadays, because it is tool you can use it in the field and where you have maybe no computer, no software, but you can use it graphical tool. So by end of this lecture, you will learn about this graphical tool. You will learn what are the different parameters which we can calculate, which is seepage, uplift pressure, and critical gradients. And then I'm going to talk about a little bit about dewatering application where we can apply. I'm going to use PowerPoint slides which are posted already on the blackboard. So as you watch this lecture, please follow the PowerPoint slides, and I will be writing certain things about that. So let's look at these PowerPoint slides. So we have chapter 8 is still groundwater, and we are looking at multi-dimensional flow and application. So what we discussed last time, the flow, and in this case we are thinking about Bernoulli's equation, and if we are interested in calculating amount of the water which can come through this pervious soil, which can be granular, which has a higher hydraulic conductivity, then it must have different total head difference. Then only the water will flow from this state or this maybe reservoir to our stream. And we can calculate that because there is a total head here at this point is much higher than total head here, and we can apply Darcy's equation if we know coefficient permeability and area of cross section. And we did do that kind of problem in the previous lecture. So keep those concepts in mind, and let's move to two-dimensional flow. So here is really a small weir resting on a pervious soil. And this is just one application of two-dimensional flow. And we want to calculate amount of discharge which will be coming from upstream to downstream, because there's a total difference, total head difference. We also want to calculate what will be uplift pressure which will be exerted on this the weir, and we want to calculate what will be the critical hydraulic gradient. Keep in mind, critical hydraulic gradient, which should be below, our hydraulic gradient should be below than the critical. Otherwise, what we have a problem we discuss in the class, that piping failure can be formed, and we will talk about that kind of failure which has happened in previous and many dams. So this is a Laplace equation. I can write this in a form of really head rather than potential, and this equation is in a two-dimensional condition. So what I am writing here is total head, and x and y are in their dimension. We can write this equation in three-dimension also. But this is a equation to solve. If we can solve this equation, we can calculate two-dimensional flow. Now this equation is only valid when Darcy's law is applicable. Means your flow has to be laminar, soil has to be fully saturated, which is a reasonable assumption to when we have soil which is below water table. And it's an important assumption is also that size of the element which we are looking at here does not change. And what it really means that soil doesn't compress or expand. We also assume that soil is homogeneous. It means that permeability of the soil in this entire soil layer is same. So if I'm looking at permeability here versus here is exactly same. That's what soil is homogeneous means. And then soil must be isotropic. And isotropic means that permeability in vertical direction and horizontal direction is same. It's not true for all kind of soil, but it's an assumption which we have to make, and only then we can solve this Laplace equation. Now, this equation can be solved and by FlowNet, which is a graphical technique, and this is what we are going to discuss in the class today or lecture today. We can solve it by electrical analogy. We can apply analytical methods, closed form solution, and we can definitely solve them using finite element and finite difference techniques, which are numerical methods. And these have becoming definitely more popular, but in this class I'm going to be not able to focus that on numerical techniques. So let me show you example of sometimes, even long time when before the graphical techniques became very common, people made the model. So here is a model of a homogeneous dam, and in this dam there's a higher water level here, means higher total head here and lower total head here. So this we call it upstream, this we call it downstream, and water is going to flow from upstream to downstream. But here we have installed some kind of filter, okay, which is kind of magnet which is going to attract the water. And what you see here is called a flow line. Water is going to be flowing. And one thing you can clearly notice that in a homogeneous media, this is a very smooth line. And it starts at almost like 90 degree and ends at 90 degree. And we can see here series of flow lines. And this is how people try to estimate what are really some of the basis of the graphical technique. This is a wonderful technique to do the modeling, but it does take a lot of effort to model different type of site conditions. So here's the case where we can use an electric potential to estimate type and kind of flow which is going to take place. So using a conductive paper and having a different charges at two surfaces, and what you see here are lines which are called equipotential lines, and it gives you a very good idea what will be the pattern. And once we have equipotential line, we can draw flow lines which are kind of perpendicular to equipotential line, and this is exactly what we do in our graphical techniques. We used to have a lab on that, but I think we just have too many labs at this point, so we have eliminated that. Now I'm going to come to what is called FlowNet. It's a graphical technique. So I want to highlight a couple of things which I'm going to show you here in this diagram. And so in a FlowNet, there are two sets of lines you will be drawing it. One set of lines are called equipotential lines. These are smooth lines, and along each of the equipotential line, total head is constant. So I want to write here total head is constant. You may have difficulty reading it, just keep in mind total head is constant means that this is like a contour line. If I take any point along this line, total head will be same. And as I come to the second line, if water is flowing from this direction, the total head here will be higher, but it will be same. So let's assume total head here is 2 meter and total head here 1.5 meter. So this is the total head is constant along each of the line, 2 meter here and 1.5 meter here. And the distance between these two lines are called equipotential drop. Okay. Now, Second set of lines are flow lines. These are also smooth lines. And the area between two consecutive flow lines is called flow channel. So this is a flow channel or flow tube. And one thing also I want you to notice that this area of or distance A and this is a distance B, in an ideal flow net, A should be equal to B. So from the graphical technique, if I want to calculate total discharge, that will be equal to K, which is a coefficient of hydraulic conductivity, L, which is length. It's not a width, it's a length. Delta H is a total head loss across the system. NF is number of flow channels or tubes. And ND is number of equipotential drops. And these are numbers. They can be partial number, they can be 3, 3.4, 4, and they have no units. And B is this distance and A is this distance. And a good flow net, B should be equal to A, so this becomes 1. So our equation for calculating discharge is multiple of permeability, length, head loss, NF and ND. And we draw the flow net to calculate NF and ND. We know permeability, we know the length, we know head drop, so therefore we can calculate the discharge. And that is one of the very important goal of drawing a flow net. Now a couple of things I want you to remember. The flow net must be drawn to the scale. And if you draw a flow net on a system which has no scale, the flow net has no meaning. The flow lines and equipotential lines should intersect as much as possible at 90 degrees. Okay, and like this. But some cases, these will not be true and you may not be able to do that. So this is the flow line, this is the equipotential line, this is a not 90 degree. Okay, so it's not always possible. Aspect ratio A over equal to B, as much as possible we should have the same aspect ratio. And the last one, we should have boundary conditions, and I'll explain it with an examples. So this is the basics of the flow net. So let's start. This is a weir, and we want to calculate the seepage through this permeable layer. This is impermeable boundary. Maybe there's a rock here, so there's a flow is very little. And this is another impermeable boundary because water cannot really flow through this weir. Okay, and I want to also you to remember this is a sheet pile made of metal, and the water cannot permeate through that. So this is my top boundary. Okay, this is all boundary, and this is the bottom boundary. So always identify what is the top boundary and what is the bottom boundary. This line where the water is going to enter right here is equipotential line, and this line is a equipotential line. This is an entrance and this is an exit. So before we start drawing a flow net, we need to identify the boundaries. Okay. So here in this figure, it's taken from your book. It shows the steps which one must follow. So after you have drawn the system to a scale, you have identified the boundaries. So this is the top equipotential line or maximum head here. This is the exit, which is again equipotential line. This is impermeable boundary, which is a flow line, and the boundary along this is another flow line. Okay. After you identify, you kind of determine how many flow channels you are going to plot. This is just starting. So in this case, for example, I have started plotting this flow line, and then I will plot this equipotential line. although in the figure, they are kind of in this book, they are suggesting that you do both flow lines and equipotential lines simultaneously. I don't think it's a very good idea. Actually, I always like to draw my flow lines first, and then I will come back and do my equipotential lines, and then I will correct them. But whatever works for you, I think that's fine. The final outcome is, as you can see here, is it has very smooth flow lines and equipotential lines. And let's count in this figure how many flow channels. Okay, so this is flow channel number 1, this is 2, this is 3. So definitely there are 3 full flow channels, but then there's a half of it. And so in order to know what fraction of the flow channel is the last one, I'm going to draw a couple of circles here. And at this point, I'm just drawing the circle by hand, but you don't need to draw by hand. And what I'm going to do is calculate what part of each of the circle is inside and what part is outside. So if I look at that and estimate, almost say 80% is inside. So this is, I'm going to call 0.8 flow channel. So my total flow channels are 3.8. So let's calculate number of equipotential drops. So that is 1, 2, 3, 4, 5, 6, 7, and 8. So equipotential drops are 8. So for this case, I can calculate Q, which is total discharge, K, and head loss times NF over ND. And I am calculating that per unit length. And let's assume length is 100 meter. So then it will be multiplied by 100 meter. And that length means perpendicular to this paper. Okay, so please don't make mistake. This is not the length. Length is perpendicular to the paper. So I need to know permeability or hydraulic conductivity. I need to know head loss, which we can calculate. And from this flow net, I just calculated NF and ND. Therefore, I can calculate discharge, and it will be in meter cube per second. Okay, meter cube per second. So here are 2 flow nets. This is the first trial, and there are a few mistakes here. So let's point out that first, you cannot have any disappearing flow lines. You must not. So this flow line is not possible, okay, because it disappears that, okay. Other thing is a common mistake that you cannot start several equipotential lines from a point. And why not? Because each of the equipotential line has a total head, and you can't have several total heads starting from one point. So although they look like starting from same point, but remember, this is a sheet pile of a given thickness. And so this is flow equipotential line from one side of the pile, this is from other side of the pile, and this is at the tip of the pile. So this is a good flow net, except I won't agree with this. So although they are calling it a finer flow net, but I will not include this line into my sketch. Now I want to point out here that you can have different flow channels and equipotential lines, and your answers can be still correct. So here is the flow net with 4 flow channels and 8 equipotential drops, and here is a flow net with 5 flow channels and 10 equipotential drops, and it will give you the same answer. So question often is asked, how many flow channels should I choose? It's really up to you. As long as you draw a full good flow net, it really doesn't matter. Your results will be correct. And all of these PowerPoint you have posted on the blackboard. So what I'm going to do, I'm going to take a break for a minute, and then I'm going to come back and draw a flow net with you, so you can see how I'm going to start drawing the flow net. So, in the last segment of the lecture, what we talked about is two-dimensional flow. And we are looking at solving Dar's or Laplace equation by different ways you can solve it. And what we are trying to learn in this class is solve it using a graphical technique, which is called FlowNet. This technique was really used by Casagrande and many famous geotechnical engineers before we had computers. And we designed many large dams all over the world using this graphical technique. So it's a simple, may look like simple and confusing technique, but it's a very powerful technique. And many observations and the looking at the shape of the flow net did not come from somebody's pigment of imagination. These engineers were observing how the water was really flowing in a real structure. Sometimes they made a model, very large number of models were made to really observe how the flow lines and equipotential lines are really should be taking shape. Now we are fortunate that we have software, we can draw that, but still, this is a tool you must use to verify your answers. I will show you in the class some of the flow nets which have been drawn by actually Arthur Casagrande and for some important dam. But I think we are going to come back now and I'm going to draw a flow net. Not the best, but at least give you an idea how to start. So this is a weir and I have drawn the sketch to the scale. So I must write the scale. A good flow net must have all the calculation right here. So if anybody looks at the sketch, all my calculations should be here. So I am going to leave a little space here. So after I want to draw a flow net here and I want to calculate three things. I want to calculate total discharge. I want to calculate maybe upward pressure which can be applied on the structure. And I want to calculate exit gradient and make sure that it's not higher than critical gradient because it will have then a piping problem. Okay, I don't think I'm going to do all of those steps now, but I'm going to start drawing the flow net. So I mentioned that first you identify your boundaries. So this is an impermeable boundary and this is what will be last seepage or flow line would look like. This boundary along this weir right here is another flow line. Okay, I don't have to redraw it, but I know that water is not going to permeate through this weir. So these are my two top flow line and bottom flow line. This surface, which is a ground surface, is my equipotential line, where the equipotential or total head is maximum. And this line is my last equipotential line where total head is really minimum. Now I need to calculate the total head loss because I would need that. And I'm going to go over that in the class, but I would define, let's say define a datum. So I'm going to define datum here and I will calculate total head at this point A and I'll calculate total head at point B. And from that, I will calculate total head at point A1, right here, the ground surface, and here at the total head at point B1. Okay, so let me go over that quickly, how to calculate total head at A. So total head at A, okay, not a very good handwriting, total head at A, and I'm writing total head, will be pressure head plus elevation head. So if I measure this distance and let me call this to the scale of, let's say, estimate that to be, let's say, 40 feet. Okay, so this is 40 feet and let's assume to the scale of that I should have plotted that is say 25 feet. Okay, so at point A, elevation head is 40 feet and pressure head here is 0 because this is a free water surface. So pressure head is 0. So the total head here is 40. If I calculate total head at point B, its elevation head is 25, pressure head is 0, so total head is 25. Now if total head is 40 here, Total head here will be again 40. And why? We discussed in the class because there's no head loss between point A and point A1. So total head here is 40. And same thing will apply when water is flowing within this water boundary. No head loss. So whatever total head is B, same will be at B1. And that will be 25 feet. So for this problem, I know the total head loss will be 40 minus 25 is 15 feet. And since total head is higher here, water is going to flow from this direction to this direction. Now after I've done that, I'm going to start drawing my first set of flow lines. And every time I teach this, there's a genuine question, where do I start this line? So I'm going to start from some distance because I think probably I'll draw 3 or 4 flow channel. Okay, so I'm going to start from here, starting 90 degree, keeping the shape of the boundary flow lines in mind, and I'm literally sketching it. Okay, and why I'm doing that? Because I will be probably erasing it maybe 5-10 times before my final flow lines or flow net is drawn. So this is my first rough flow line. I'll start the second one from little distance farther, and that may be my second flow line. And I'm not sure I can really fit a third, but let me try and see if I can fit the third flow line. And let's assume that they're pretty good. Okay, so now I have to draw an equipotential line, and what I'm going to do to draw that, I'm going to draw a circle. Okay, and to get an idea how do I get started with my equipotential line. So I'm drawing a circle. They don't have to be same size, and I'm going to start my equipotential line like this, starting at 90 degree, and I will move down. Okay, and I started from upstream, and I'm going now downstream, and as much as possible I'm starting with 90 degree angle. So these are 90 degree. I'm trying to meet at 90 degree, and as I'm going to come down, the shapes are still not rectangle. Okay, this is not 90 degrees, so I correct it, and maybe like this. Okay, so this is not a wonderful flow net, but it needs to be corrected several times. So after I have done this flow net, I'm going to now go back and adjust my flow line, then adjust my equipotential lines, and then after I am satisfied, I'm going to talk about how do you know what is a good flow net. Then I will calculate what are my number of flow channels and number of equipotential drops, and then I can calculate the discharge. So let me show you for the same one a good flow net. Okay, this is in your PowerPoint presentation. So forget about this part, just focus on this lower part. And this is a pretty good flow net, very good flow net. So all the lines smooth, they are intersecting at 90 degree. In many of these grids I can fit circles. So this is a final flow net, and from that I can calculate total discharge. So I hope it is clear to you what are the steps. We are going to go over some of these things in the lab, so and you will practice it, so you will get perfect. Now let me go over other things which is really wonderful from the flow net we can calculate. For these kind of structures, we are always interested in calculating uplift pressure, because we don't want the structure to fail. And in order for me to calculate uplift pressure, I need to know what are the pore water pressure at point A, B, C, D, E, and F. And I can do that using the flow net. So how would I do that? suppose I'm interested in calculating pressure at point B. All I need to do is calculate pressure head along this line and multiply pressure head by unit weight of water, and that will be giving me pore water pressure, and that's your pressure uplift pressure. Same thing, I can do it here, calculate pressure head and then multiply it by unit weight of water, and that will give me uplift pressure. Now, how do we calculate pressure head here? Because these are the lines of total head. But that's simple. If I know the total head along this line, I can subtract from that elevation head. That will give me pressure head. And then once I have pressure head, it's easy to calculate uplift pressure. The table which is given right here shows some of these calculations, because it is showing at point A, number of drops are 1, 2, 3, 4, 5, around 5.5 drops have taken place. I know how much total head will be because of 5.5 total head. So I know the head loss, and I subtract that from the total head. That will give me total head along point A. Subtract from that elevation head. That will give me the pressure head. Pressure head multiplied by unit weight of water gives you uplift pressure. Okay. We are going to go over these calculations in the lab. You are going to be calculating this for project 3, which is the most important part of the project. And the last part I'm going to go over with this on this figure is how to calculate exit gradient, okay, or discharge gradient. For discharge gradient, you always look at the last grid from which the water is coming. We know what is the total head loss, which is around 0.93 feet, which we calculated. You measure this average distance and convert it, multiplied by scale. So that is 4.2 feet. That's 4.2 feet. Ratio of these two gives you exit gradient, and this must be smaller than critical gradient. And when it doesn't happen, then we have the piping problem. Okay, so let me summarize what we just calculated from this flow net. We calculated discharge, we calculated uplift pressure, and we calculated exit gradient to ensure there's no piping problem. Okay, so this is wonderful because we can calculate quite a bit information. Okay. Now, how do we really check the flow net is good? And this is the technique which is used. And what really ensured by using this, plotting these circles of different size, that we are saying A is equal to B, because this is our assumption. So I want to point out, look at each of the circle here are not same size. And this is a symmetrical flow net, so you can have these two circles the same diameter. If you can fit in your flow net in 60% of your grid a circle touching all four sides, it is a very good flow net. So this is a check. I think you won't be able to fit in all the grids, but 60% of them. And I want to see that when you plot your flow net, I want to see that you will be able to fit some circles or not. Now, in the next couple of figures, I'm going to show you a typical flow nets. This is very important to collect this kind of data with you, because when we have projects and we have no idea how to start, I save them. I have a library of different flow nets and save them, and it gives me an idea what is the shape of that. So here is a masonry dam resting on a very pervious foundation, and this is a wonderful flow net, and suppose this quantity Q comes out to be very large. Then as an engineer, you have to look at different ways how you can reduce the seepage. So in this case, some sheet piles upstream and downstreams are placed, and a graded salt filter is placed downstream. And now you can see the shape of the flow net changed, and what it really changed is number of equipotential lines are increased, and because of that your new discharge Q1 will be less than Q. Okay, and we can calculate that using the flow net. Here's another option. Instead of having the sheet piles on both sides, we have sheet piles only upstream, and then we have a large filter downstream. This is a very good design because the amount of water will be reduced, but it will be collected in the filter, and we will go over the design of filter, and if the filters are well designed and constructed, then you really eliminate the problem of soil piping. Okay, and these options are evaluated and still evaluated using flow net or numerical techniques before we implement any of these options. And not only we evaluate different options, we then calculate the cost for implementing every option. Okay. Now your design project is going to be something like this, and it's really very, very interesting project, and I think I've taken this figure from the book, and you will be plotting flow nets looking at different sheet pile depth option. So I'm going to leave this figure for later because you will spend a lot of time, and hopefully you will come up with a wonderful flow net. And I found similar kind of case in another book, a flow net. I don't agree with this flow net because I don't think there should be a sharp edges like that. But I just want you to caution you, because you may find in particularly on website many of these drawn flow net. It doesn't mean that they are correct. Okay, so not everything you find is really that you say this is correct. There are lots of mistakes in this flow net, and I want you to point out. I will talk about in the class, maybe in the test. So the last segment where we looked at really how we draw a flow net, we talked about from the flow net, we can calculate total discharge, we can calculate uplift pressure, we can calculate exit gradient and compare to critical gradient. But remember always that flow net can be only drawn when the soils are homogeneous and isotropic. Now, certain soils, particularly alluvial soils, which we often found in the foundation of the dams particularly, are not really isotropic. And often the permeability in horizontal direction is much larger than permeability in the vertical direction. It is the nature how the sediments were deposited. So it means soils are going to be anisotropic. And can we apply this technique to draw flow net on an anisotropic soil condition? So I'm going to show you a case here. So in this segment of my lecture, I'm going to talk about two things. One, I'm going to briefly talk about anisotropic soil condition, and then we will talk about what happens when exit gradient is higher than critical gradient. And then I am going to kind of switch and talk about construction dewatering. And why that is important, because your project 3 is a very interesting project in downtown Syracuse near the Destiny Mall about pump station. And the whole project, the premises of the project is calculate the discharge for a pump station. So I'm going to talk about that. Okay, so let's start with the anisotropic soil condition. Okay, so here is the flow net, which has been drawn in a case of a sheet pile being driven in a soil which is homogeneous. Okay, so this is our reference line. But if we have the flow, which is permeability in horizontal direction, is 4 times the permeability in vertical direction, as you can see, the flow net is completely as if you have stretched in horizontal direction, or if you have drawn it on a more like elastic paper and stretched in a horizontal direction 4 times. And you can see that it's much easier for water to flow in a horizontal direction than vertical direction. And here is the case where the permeability in horizontal direction is 9 times the vertical permeability, and you can see is further stretched. So how we draw the flow net in this case is that we take the transformed section and we convert it, okay, in an hypothetical isotropic section, okay, and then we draw the flow net for that isotropic cross section, and then we convert it back to real situation. But when we calculate the discharge, instead of using horizontal or vertical permeability, we apply this average permeability. Okay, so we look at the permeability in horizontal direction, vertical direction, head loss, NF over ND. Okay, we will not be spending a lot of time in this class to really plotting flow net for anisotropic. It's pretty complicated, and I'll be very happy if we can just learn about isotropic soil condition. So let me refresh your memory about Teton Dam project. We discussed this in the first day of class. Teton Dam is a very important project from the geotechnical point of view, because this is the first or maybe largest earth dam which failed on its first filling. So it's it was a 305 feet dam. It was built over a year of 4 or 5 years, but it failed in morning of June 5th in 1976. And there are a lot of actually figures and YouTube you can find, and I'll send you that website where you can see this failure taking place. So this is one of the figure from this database, and what you can see the figures, the reservoir really gushing downstream, washing away this part of the dam, and eventually 1/3 of the dam was completely washed in a couple of hours. Now there were many reasons for such a failure, but one of the reasons definitely was soil piping, and which is initiation of when the hydraulic gradients become higher than critical gradient, soil loses its strength, and this phenomena we call piping. Okay, this is what happened, and this was definitely one of the reasons. This is one slide which I showed you again first day of class. Here is a levee and there's a road, you can see a car there. This part of the levee completely washed away. Okay, this is not during hurricane, but this is due to piping phenomena. And again, when hydraulic gradients become greater or equal to critical gradient, soil piping happens. And this is a very important aspect of design which we have to pay attention to. So now I am going to move to another important topic, and it's briefly discussed in your chapter 8. And that is temporary construction dewatering. So there are many different ways to do the dewatering. And there are open pumping, pre-drainage, cutoff, and exclusion. And I'm going to briefly talk about each of them. And which one to select for one project depends on definitely soil. Whether your soil are granular, say sand and gravel, or low permeability, silt and clay. Size of construction, whether small excavation or excavation for a very large foundation, such as what happened in Destiny Mall when they built the foundation. Proximity of other excavation. You don't want to disturb other buildings and other conditions, so we need to keep that in mind. Type of structure built, and whether your water which is going to be coming in your opening or construction is going to be contaminated or not, because you have to really then address what are you going to do with that water. So let's start with open pumping. Okay. Now here's the sketch which I want you to look at that. So here's excavation, and we need it for maybe pouring a foundation, or we are going to lay a pipe here. But in this case, we allow the water. So this is our original groundwater table, and water will start seeping in as soon as you make this excavation. We allow the water to come in, but we remove the water from the sump area by installing pump, and then water is taken out. Okay. This technique is very good when we have soil of low permeability and which is silt and clay, because the amount of water entering this excavation is not very large, and your side slope will remain stable, so you don't have to do shoring and provide the support. If you have highly permeable soil, this is not a good technique. Now let's look at the techniques which are preferred for more permeable soil. So in this case, this is excavation and this is original groundwater table. So we use different techniques and maybe series of pumps which are installed around this excavation and which allows us to lower the water table. So now water table is lowered below the excavation. So this is all now dry surface. We can do construction, we can lay pipe, and there's no problem with that. And this lowering of water table will continue to take place as long as excavation is open. So this is a wonderful technique, and we can remove this water by a pumped well system where we install submersible pump in each of the well, and this is expensive. Or we can have series of well points around this excavation, but that is only limited when we need to lower water table up to 5 to 6 meters. Okay, so keep that in mind. This is an example of one of this technique we just mentioned, pre-drainage. So here is a open excavation, not very deep but fairly large. We are installing these pipes, maybe these are gas pipes, and you can see that series of pumps here. Okay, series of pumps have been installed here and wells, and the water is being drained out or lowered out. So there's no water here at the base of this foundation. So this is working very well. So this is excavation used a pump well system. Now another technique is really in this we don't allow the water to come to this excavation, and which is called cutoff technique. So we can install series of cutoffs around this periphery of excavation, and we can still have some pumps. So if a small amount of water still comes, which is very limited, we can pump that one out. But our goal is to really not allow the water to come in. So once the water table is lowered and we install the cutoff, we have really kept this water out. Now, so we are blocking the water to enter. And there are many different ways we can install these cutoff wall. There are many different type of cutoff wall, and I'll give you an example of some. So type of cutoff walls can be steel sheet piles. This is a very common method, and for 50 or 100 years we are using it. Very effective method. Diaphragm walls is becoming a more popular. Slurry trench is a very economical method, widely used. This secant drill shaft walls are a little new technique, and this is definitely totally new technique. Ground freezing is that you freeze the entire ground. It's a very expensive technique. In fact, almost 20 years ago in Syracuse, I saw this technique being used, and since then I've never seen any project where they have used locally this technique, because this is not just a winter, the construction is taking place in the summertime too. So let me show you steel sheet piles, what they look like. These are generally heavy corrugated sheet piles which are driven vertically, and they are interconnected. This is very important, they have to be interconnected, and they are pushed in the ground with a vibration. And these seals between these series of these piles are sealed. So this makes a very impermeable wall, as you can see these being installed, you can have different water level here, and if they have done very well, this is a very impermeable cutoff technique. And the project which we are going to work on, which is project 3, they used this technique. And last picture which I have here is a slurry wall, which is again very common technique. So I want to briefly explain to you what is a slurry wall. So slurry wall typically is an excavation in the ground of 2 to 3 feet wide. This can be very deep, 20-30 feet, and we remove the original soil and backfill the soil with either soil bentonite and cement. And bentonite, you remember, it's a montmorillonite which swells. And by filling it with low permeability material, particularly clay, montmorillonite and cement, you are creating a wall of a low permeability, and which will work also as a cutoff. I can think of several projects, including in near Syracuse, and where slurry walls are commonly used as a cutoff wall. So this is a topic of the cutoff walls, and drainage is a topic which can really, entire course can be taught, but unfortunately we won't be teaching that. But we are going to apply some of these concepts for our project 3, because this is a really very important part. Hi everyone. So in this recorded lecture, 3 segments which we covered today. So first part was really solving Laplace equation using graphical techniques. And the second, I really tried to teach you how to draw a flow net, which is a graphical technique to solve Laplace equation. It's a very powerful technique, as I probably stated many times, because you can calculate total discharge, you can calculate hydraulic exit gradient, you can calculate uplift pressure, and you will be calculating all these quantities and values for the project. And third part of this element of my recorded lecture was talking about construction dewatering. That's also part of the project, related to part of the project. I want to point out one more thing which we discussed in chapter 7. One of the parameter we need to calculate, particularly discharge, is soil hydraulic conductivity. This is one of the most difficult property of the soil, as you will learn from this project. Sometimes we don't have really much data to estimate that, and we can't take small samples from the field and perform this test, because it's not going to give you reliable value. In this project, project 3, they did only one pumping test, and we have only that data available. We have something, I'm going to give you grain size distribution for you to estimate the permeability. So one of the challenge for this project, and particularly for the owner of the project, is how reliably can we calculate the discharges. Okay, so we are going to have wonderful discussion. I hope you're watching this and taking notes, and because I'm counting on it. Thank you.